Welcome to Simple Physics. In this video, you will learn about the laws of refraction. A ray of light traveling from air to water bends towards the normal. The bending is greater when the same ray travels from air to glass. It is obvious that the amount of refraction would be different for different materials. The phenomenon of refraction of light was studied in great detail by the 16th century Dutch physicist and mathematician, Willebrord Snellius, known to the English-speaking world as Snell. After experimenting with a number of transparent materials, Snell postulated the laws of refraction. The first law of refraction states that the incident ray, refracted ray, and the normal lie on the same plane. The second law states that the ratio between the sine of angle of incidence and the sine of angle of refraction is constant for any material. It is possible to verify these laws by conducting an experiment. In this experiment, a ray of light is made to travel from air to glass, and the relationship between the angle of incidence, I, and the angle of refraction, R, is investigated. It is observed that as the angle of incidence is increased, the angle of refraction increases as well. The values of the sine of angle of incidence and the sine of the angle of refraction are then plotted on a graph. Since the graph is a straight line, it can be concluded that the sine of the angle of incidence is directly proportional to the sine of the angle of refraction. This implies that sin I is equal to mu sin R. Here mu is a constant, and mu is equal to sin I upon sin R. Hence, the second statement of the laws of refraction is verified. The constant mu is said to be the refractive index of the medium consisting of the angle of refraction, R, with respect to the medium consisting of the angle of incidence, I. Being a ratio, the refractive index nu does not have any units. To understand the meaning of refractive index, let us consider a ray of light moving from medium 1 to medium 2. We already know that mu is equal to sin I upon sin R. The refractive index of medium 2 with respect to medium 1 would be written as 1 mu 2. Since the angle of incidence is A, and the angle of refraction is B, 1 mu 2 would be equal to sin A upon sin B. Similarly, the refractive index of medium 1 with respect to medium 2 would be written as 2 mu 1. And this would be equal to sin B upon sin A. When a ray of light travels from medium 1 to medium 2, its speed changes from v1 to v2. The refractive index can then be expressed as a ratio of the speeds of light in both the mediums. Hence, 1 mu 2 is equal to v1 upon v2, where 1 mu 2 is the refractive index of medium 2 with respect to medium 1. Similarly, 2 mu 1 is equal to v2 upon v1, where 2 mu 1 is the refractive index of medium 1 with respect to medium 2. If a ray of light travels from air or vacuum to glass, the refractive index of glass, with respect to air, would be A mu g. Now, whenever the refractive index of a medium is expressed with respect to air or vacuum, it is said to be its absolute refractive index. The absolute refractive index of a medium is defined as the ratio between the speed of light in vacuum or air, and the speed of light in that medium. If the speed of light in air of vacuum is c, and the speed of light in glass is v, the absolute refractive index of glass, mu g, is equal to c upon v. The speed of light in vacuum is 3 × 10⁸ meters per second, and the speed of light in glass is 2 × 10⁸ meters per second. As a result, the absolute refractive index of glass is equal to 1.5. This table shows the values of absolute refractive index for air, water, glass, and diamond. Since the absolute refractive index of diamond is the greatest, a ray of light traveling from air to diamond will suffer the greatest amount of refraction. While the refractive index of different materials is different, it is observed that for the same material, the refractive index is different with different wavelengths of incident light. Consider this. The wavelength of violet light is 4000 angstrom. This is lesser than the wavelength of red light, which is 8000 angstrom. However, a ray of violet light, traveling from air to glass, suffers a greater amount of refraction, compared to a ray of red light. This means that the refractive index of glass is greater for violet light, and lesser for red light. And now, the summary of this video. 1. Light obeys Snell's laws of refraction. 2. The ratio of sin I to sin R is called refractive index. 3. Refractive index is also a ratio of the speed of light in both mediums. 4. The ratio of speed of light in vacuum to speed of light in a medium is called the absolute refractive index of the medium. 5. The refractive index of a material is greater for lesser wavelengths of incident light and lesser for greater wavelengths of incident light. That's all about the laws of refraction. In the next video, you will learn about the effects of refraction.